Hey everyone, well, I'm excited to be here at the DC Kubernetes meetup for Kubernetes. Today I'm actually talking about a little different area from what Kubernetes is known for, which is actually scheduling scientific workloads, such as batch workloads, across multiple Kubernetes clusters at once. Armada is a project I'm going to be presenting, and we were just recently accepted into the Cloud Native Computing Foundation as a sandbox project as of, I think, 1 month ago. So you won't see it on the website yet, but stay tuned on that one. So to go in, my name is Kevin Hannon, and I work for G Research as part of their open source division, where their focus is on enabling and contributing to communities that they utilize in their work. So I'm actually focused mostly in the Kubernetes community and enabling batch workloads in Kubernetes. I actually kind of started my career in more of the scientific computing space, and this is where I got an interest in this. My last role before this one was actually working as a contractor for the National Institutes of Health, trying to enable the researchers and the data scientists to run scientific workflows across either high-performance computing clusters on-prem or trying to use Kubernetes to schedule container jobs. So I kind of took this role at G Research because I was really interested in Kubernetes and seeing how I can contribute to allow Kubernetes to be a better platform for scientific researchers or even just more research focus. So G Research is actually a London-based company that just opened their first US location in Dallas as of, I think, this year. But for the purpose of this talk, the primary reason why they created Armada was they wanted to build a research platform on Kubernetes that allows for their quantitative analysts and other types of workers at G Research to submit calculations and to have a general cluster for them to work with. So to start off with, what is batch processing? For me, I like to just a pretty simple definition, just a finite job that usually runs on the order of minutes to weeks, and typically it is you run a container job, and then once it finishes, it writes out the data. Once that job is removed, and usually Kubernetes will delete that pod. And so there's a lot of areas. Obviously, if you're from the tech space, you've heard of AI, machine learning, some other areas that are closer to my heart, because my background was, my PhD was in computational chemistry, so I learned a lot about how to use computers and simulations to model molecular problems. So that's kind of what I have to focus on that in this slide. So computational science can be modeled as a batch job because usually it's some kind of, you specify some parameters, run some kind of executable that usually utilizes a lot of parallel computing resources, and then you get out some data from that. Some other areas are also pretty common in IT in the tech world is extract, transform, load, or extract, load, transform data workloads, reading data from the Spark cluster and processing it and then loading it to a cloud storage service. I did not know this area as well as I did when I joined the National Institutes of Health, but genomics is also another interesting area for gene sequencing that actually has a lot of utility in using containerization and batch jobs, and there's actually a large following there about trying to utilize Kubernetes workloads in the genomics community. So these are all common ways of using batch, and I want to show a couple more than what most people know. So to kind of level set, there are kind of two areas of parallel computing that I think of. Number one is just a very simple, embarrassingly parallel type of workload where you have this idea of you can split your workloads into multiple different parallel steps, and there is no communication between any of the processes. And then pretty much once that process writes out its data or does something, you can kind of gather that data in some kind of one process that allows communication. So this is really easy to work in Kubernetes, because as I will explain later, Kubernetes does actually natively support this. The one that is more challenging is when you actually want communication between your processes. This is a common pattern in high performance computing, or so you can imagine like what I mentioned with like protein folding or something, or really a program that uses some kind of framework that allows for communication between different processes. A popular term that is used in the high performance computing area is called the message passing interface, which is MPI. This is a pretty old framework compiler. It's really invasive if you've ever worked with it. It kind of permeates everywhere in your code. But it is primarily for passing messages between processes, whether it's in a node or internode, and also there are possibilities of using GPU to GPU communication. So this is what is kind of hard to model into Kubernetes. It is possible to do this, but it's not the most effortless. It's not really easy to do. So, in general, how do researchers, what is a research platform in my eyes? Usually it is a user kind of SSH into a login node, and then they kind of run some kind of script that schedules their job, and typically you have some kind of scheduler that puts your job in a queue, and then if all your nodes are taken up by doing their compute, your job has to wait until that node is free. And then typically these nodes, the way they're more performant than normal is they usually have some kind of network that allows you, a high-speed network that allows you to communicate faster than you would from general TCP or HTTP requests. And then usually for at the NIH, where I worked before, they have a kind of general programs that are preloaded on researchers can use, and it is actually bringing containers into that general. This is kind of a pattern where you have executables that people want to run. They can load them into and execute their job. Kind of what a research platform is. Some two areas, and I'm talking about Slurm and HT Condor, which are ways to run jobs on computing clusters. Slurm is one now. HT Condor, because G-Research was actually originally an HT Condor farm. So in general, these all kind of have similar metadata. Or what partition do you want your compute nodes per node do you want, and how long your job's going to run, and then what kind of execute. Some areas that are also kind of migrating to Kubernetes are able to run these, but usually you have to specify log files and error files. But if you're familiar with Docker or Kubernetes, it's usually you can run, but it's a challenge to map these. HT Condor, similar thing. So the supercomputing group releases a list of the computers every 6 months. European Supercomputing Conference, they released in June in Europe. The number one fastest computer in the world is Frontier National Lab in Oak Ridge. I'm mostly showing this wanted to build with Kubernetes. You have to target around, these are obviously state of the art, but typically these are around 8 points. And that compute power, I actually put the number of on these machines. Should have looked that up beforehand. But in general, what they kind of journey to Kubernetes were primarily a company, and they were using HT Condor to schedule high throughput jobs. It is a lot more data analytics on Linux and containerization, so that there's been a focus to try and migrate more of their existing containers, and this was probably a big focus. As we all know, Kubernetes Workloads now too. But in general, the goal is to try to adopt researchers to use containers, have a place. One of the main Kubernetes is there is actually no queuing solution currently in Kubernetes. And this is this idea that you have more requesting jobs, and you have to queue your jobs and wait for complete. One of their goals was to build a cluster that has roughly 100,000 nodes and about 1 million core GPUs, or some enable deep learning workflows where they want to utilize GPUs. For high throughput of around 10,000 jobs over a short amount of time, and they want to be able to schedule a node and a wide range of user research. So they have a way for users to submit jobs, and also for administrators to have an idea of what's going on, what jobs are stuck. So Kubernetes, you can do for scheduling a job API, which is a job is a controller over a pod, really, based off pods. A job it kind of does function the way a batch job, or once that job finishes running, the job controller will remove that pod, so the API can't store that anymore. One of the problems with doing that, it's hard to schedule a lot of jobs at once with Kubernetes, and it is actually really tricky for nodes on Kubernetes. This is an AI that actually talks about with trying to run Kubernetes to 7,500 nodes. There's also a really good doc on the Kubernetes website for talking about how to run Kubernetes at large scale, and at G Research, they actually do everything on-prem, so they're not using a managed service, so a lot of times it is a lot of maintenance headache to try to maintain a lot of these nodes. The other issue with the job API that I forgot to mention is that there's not really a great way to do parallel jobs where communication is required, because typically these pods are scheduled. The Kubernetes schedules an individual pod. It does not really schedule a group of pods that can communicate together and what that is called in this community is called gang scheduling, or all or nothing scheduling, which I will talk about different ways to approach that. So in general, Volcano is a further along project than Armada in the CNCF landscape. I think they are now an incubating project, and their philosophy for designing this work was to actually extend Kubernetes via custom resource definitions, or CRDs. Volcano is actually a single cluster, and they have pretty much forked their own scheduler in order to work with their own CRDs, and won't talk too much. I have one more slide about Volcano, and I'll talk more about that one. And then Armada is obviously the one I'm talking about today, where our focus is on trying to enable it with multiple Kubernetes clusters and trying not to change the Kubernetes scheduler, and we also provide our own queuing logic. So Volcano has 3 custom resource definitions that are useful for this talk to know about. They're job, pod group, and queue. Queue is their implementation of how to support queuing logic in Kubernetes. And then job and pod group is actually how they do their set of pods that get scheduled together, so they can run a parallel job that allows for making sure that if one pod can't get scheduled, it holds the group until the rest of them can be scheduled. And then they also found that the initial job API was not exactly what they needed, so they created their own CRD to represent jobs. Well, for Armada, one of the reasons why we want to take this approach to do multiple Kubernetes clusters was primarily to be able to support multi-cloud, and also to be able to have this idea of if you can maybe deploy a change to one cluster at a time to verify how things are going to behave or make sure things don't work, and also you don't want to take down your entire cluster with a bad config change. And so another focus was trying to be as close to Kubernetes as possible, because Kubernetes is a great community that is very active, and we want to make sure that it's not a lot of effort to upgrade Kubernetes, and also we want to keep utilizing the community when we can. So for main concepts that you have to know for when we talk about Armada, a job in our case is actually a grouping of Kubernetes resources, so pod specs, ingress, and we also allow you to create services. The reason why is we may want to actually have networking when we schedule a pod. Another area that they focused on is job sets, which is this concept that users really actually manage. They usually submit a grouping of jobs that are going to be run, and then they're allowed to subscribe to an individual. They're allowed to subscribe to an individual group of jobs and be notified when their jobs are completed, rather than one by one polling of a job. And then queue, as I've mentioned, is a way for people to schedule how your jobs get queued in a priority list. We have a user guide that kind of goes into more details, and I will talk more about usability of this later. So Armada, the way we break down our architecture is we have a general API that users can submit to a server, and that stores events and jobs, and that is in a Kubernetes cluster in itself. And then we have what we call executors, which are Kubernetes workers that are allowed. That's actually where pods are run, and that's how you actually scale out and add more clusters. And so now you have And one of the reasons why they also approach this way is they want to be able to make this resilient to node failures and also be able to add and remove Kubernetes clusters if they want. So queues are, these are pretty simple. We have our own API for scheduling queues that also allows for role-based access control. G-Research has a pretty, they have a lot of interest in keeping certain things in certain groups so they can view what's going on, and this is why role-based access control is super important, and for us and also for a lot of people. But in general, a queue has both resource limits and priority factor. And then the job spec, if for everyone here probably has seen a pod spec, it's very similar. It's basically a container. And then we also have a little bit of metadata that allows you to schedule stuff like labels and annotations. And then we have concepts like ingress and services to enable networking with our pods. And then usually a job requires a queue and a job set. And what's nice about utilizing the Kubernetes API, we can actually add commonly used Kubernetes resources that allow you to schedule jobs to GPUs, which are taints and tolerations, to actually get your job to run on a particular node that has a GPU. And all this is available as part of the pod spec, which is actually what we take from Kubernetes. So our users typically interact with Armada via a couple gRPC clients. We have a .NET client, a Python client, a Go client, and a CLI that allows you to run, to allow to submit jobs and create queues. I just have a snippet of code here, which is an API, which is the Python client that we just recently released, which allows you to create queues and submit jobs. One integration that I helped work on was actually enabling Apache Airflow and Armada. For those that are not familiar, Airflow is a task-based system that orchestrates running, really, it's a Python-based task orchestration software that allows you to run different tasks. The paradigm for Airflow is that in order to add a new ability for Airflow to interact with other platforms, you can create something called an operator. And we created an Armada operator that allows you to, using Airflow's UI and their syntax, you can create a DAG that will actually run your application on Armada and have the Airflow scheduler sort of manage when to schedule these jobs. I have the figure I have here is just a simple example of making sure the error logic of Armada, like this is a DAG where you have two parallel tasks and you want to run a job downstream, but if one or the other job fails, you don't want to run the downstream job. This is all handled by Airflow. Again, the Armada operator is the Airflow operator, this is syntax for Airflow, so it's how you can specify a DAG, and this is what would be the API if you wanted to use the Armada operator in Airflow. Another project that it has been done internally is to allow our users to submit interactive jobs in the high-performance computing space. There's actually a way for users to request an interactive job, so they can say, I want this node for X amount of time, and then they're able to log into that node and run some kind of batch job or run anything really in there. And G-Research does have a pretty huge focus on data science and analytics. So they actually had a request to enable Jupyter, which for those that are not familiar, Jupyter is a interactive notebook environment in Python. It's actually not as many people know this, but Jupyter also allows integrations with other languages like R, Python. There is some .NET interactive ability with Jupyter, and I haven't seen the C++ one, which is crazy to me. But anyway, usually the way it works is that a user can submit a Jupyter pod, and then the reason why we added stuff like ingress and services was we want to be able that once they submit that pod and it's queued up and running, we want our users to be able to open up a browser that points to a Jupyter notebook on the cluster so they can take advantage of the compute resources. And this is open source, and I just have a simple example showing kind of what this would look like, because with our Python client, we are actually able to schedule this job, and since we have ingress and services available in our API, this is actually pretty effortlessly enabled. So I talked about admin and usability. Well, we also have created a React UI that allows you to monitor what jobs are running in the queue. We have 3 views for our we call it Lookout. It's a React UI based off Material UI that allows for an overview, job sets, and jobs. The top view here is actually allowing you to view the state of the world via the job sets. So this allows you to, we're going to be continuously adding to this to give more features to our users, but it allows you to know what queue it's running on, what's the state of your job, and then if you click on the job ID, you can drill down and get more details, like what resources your job had, what state. There's also, I didn't show it here, but you also can see the YAML of the job that you submitted. And then, so what's next for us is one main thing we're focused on is enabling gang scheduling, which is all or nothing scheduling, so allow grouping of jobs allow grouping of pods to run together, and that should enable better support for MPI and Dask and Ray and other types of workloads that are more, that require more resources. Preemption, which is this idea of higher priority jobs. You should stop lower priority jobs so higher priority jobs can run ahead of them. We're always adding more support for our users to be able to have a better idea of what's going on and adding more information, because it is hard to take people that are used to HT Condor or more of like a batch and move to Kubernetes, understand what events are, so we can kind of see. We're also always looking for more integrations with other open source software, some of the stuff that we're doing, and AI Kubernetes community. So this is actually for me, but I want to give a little shout out to a couple areas that if you're interested in this, this is attraction, because as to realize that the Kubernetes quite fit for batch. The top bullet point here is actually a working group that is focused in Kubernetes for enhancing the queuing workload to Kubernetes, and then also enables. I have a link here that is one of the major things they just released, which is a Kubernetes CRD for this. And they are kind of a mix and match of different Kubernetes groups. I think there's a special interest group called Special, and I think Signode are all enhancing Kubernetes, so getting involved and learning more. We are also part of the CNCF batch working group, which is more a higher level best practices for how to run in Kubernetes, and a lot of, in my opinion, this that is spread across the world, and you have to look at blog posts and implementers to actually understand the do's and nots for this place for people to read and scour blogs. Also, we are on GitHub, and we just have CNCF. We are actually, so if you are learning more about Armada, you can check us at the Cloud Native Computing Foundation under Armada, or if you just want to take a look at the code, research Armada, that's all. So.